Hello everyone, and thank you for attending today's webinar. On behalf of BIS Research, I would like to welcome you all on our webinar on sustainable steel, a clean energy transition. This is Priyanka, Senior Research Associate in Advanced Materials and Chemicals at BIS Research, and I will be the moderator for today's webinar. BIS Research is a leading global market intelligence research and advisory company that focuses on emerging trends in technology which are likely to disrupt the dynamics of the market. The mission is to harness the potential of disruptive technologies to make businesses thrive in today's digital age. For today's webinar, we have an esteemed list of speakers. Firstly, we have Ms. Troy Coyle. She is the CEO of Hera. She brings more than 20 years of experience in innovation management covering the private sector, non-profit organizations, government, and academics across a range of industries including material science, medical radiation physics, sustainable building products, and steel, among others. She can be the best described as an innovation research leader who has worked in steel based research for a long time now. Currently, she is the director of HERA certifications, a board member of the Sustainable Steel Council, director of the Construction Industry Council, and pro vice chancellor advisory board co-chair of Hanga Aurora Workforce Development Council for Manufacturing, Engineering and Logistic Workforce Development Council, and member of Ministry of Business, Innovation and Employment Building Advisory Panel. Next, we have with us Mr. Daanish Ellias, founder of World of Steel, who brings more than 30 years of experience in the global steel trade with an inclination towards every facet of the steel trade. The manufacturing process, the global macro factors that affect steel pricing and its trade, and of course, the future evaluation of steel making and its trade. World of Steel is a reservoir of his journey and his online avatar. It allows him and his team to offer global marketing solutions and logistics for flat as well as long steel. It also offers casting and exhibit fasteners with a well-developed supply chain for sourcing, inspection, and sales to satisfy customers across the globe. Today, Mr. Daanish is accompanied by two of his teammates, Harasis Kaur and Siddhi Gaikwad, who will be assisting Mr. Daanish in his presentation on sustainable steel. Harasis Kaur and Siddhi Gaikwad are pursuing their studies from IIT Mumbai. Also, we have with us Mr. Sachin Singh. Sachin is the lead analyst of the Advanced Materials and Chemicals vertical at BIS Research. He has over 6 years of experience in bulk and specialty chemicals, sustainability, agrochemicals, petrochemicals, plastics, and polymers, and others. He has worked on more than 16 market intelligence reports, custom studies, and oversees the presentation of market developments and technologies across advanced materials and chemicals domain. And we have with us Ms. Komal Yadav. She is research analyst in the Advanced Materials and Chemicals vertical at BIS Research. Her expertise lies in the field of chemical and materials, oil and gas, and sustainable technologies. With a keen focus on sustainability, she has closely monitored advancement in sustainable technologies for approximately 4.5 years. She has been involved in publishing over 30 technical and market intelligence reports, as well as custom studies and client presentations focused on various emerging technologies. I thank all the panelists for their gracious presence. So let's discuss the agenda for today's webinar. We will start by highlighting the major energy intensive industries, steel industry scenario, and sustainable steel market dynamics, development, and market scenario. In the next 40 minutes, We are all keen to learn from your experience about sustainable steel, and towards the end of the discussion, I will open the panel to the audience for any questions. I would like to request speakers to kindly mute their phones, and during the presentation, the audience can type in the questions in the chat box, and we will be answering those at the end of webinar. Any question that we are not able to answer today shall be reverted in a blog post or through email. So now let's discuss the key agenda of this webinar. The key agenda are to evaluate market dynamics in sustainable steel industry, to analyze the initiatives taken and favorable policies to promote sustainable steel, to analyze the key technologies for the sustainable production of steel, to evaluate the major players, the sustainable steel industry. Now, let me open the panel for discussion and invite thoughts for discussion from Mr. Sachin Singh. Over to you, Sachin.
Thank you so much for the introduction, Priyanka. I would like to warmly welcome the audience and our esteemed speakers. Thank you for your valuable presence and time. Now let's talk about sustainable steel and rising need to reduce harmful emissions from the steel industry. Industrial pollution is a worldwide issue. Its negative impacts are increasing, and various organizations and individuals are working to reduce the carbon footprints. Now, as we go to the next slide, so here we have given an overview on major energy intensive industries, and we found out that steel industry contributes to the largest share of CO2 emissions compared to other two major energy intensive industries. Thus, decarbonization of steel industry is a top priority to attain carbon neutrality targets. Recycled steel and green steel are the two product types, that contributes to the sustainable production of steel with lower carbon footprints compared to traditional steel making. Currently, recycled steel is dominantly being used and is expected to keep its dominance in the next decade or so. If we talk about green steel is at the very early stages of commercialization currently, but is expected to grow at a rapid rate in the next decade as companies are investing more in the production of green steel and are planning to switch from conventional blast furnaces method to greener methods, utilizing sources such as green hydrogen and direct electrification. Next slide, please. In this, we have talked about increasing trend in crude steel production and decreasing trend in the carbon emissions from the steel production as we go till the year 2030. The major reason being growing investments in the advanced sustainable technology, that is scrap-based electric arc furnace. Also in the future, there will be increasing adoption of hydrogen direct reduction technology in the future. Can we move to the next slide, please? Yes. So currently, as you can see, emission intensive basic oxygen furnace technology is leading in terms of global operating steel production, followed by other technologies such as electric arc furnace, mixed methods, and open hearth furnace. But the share of sustainable steel production technologies is expected to grow at a higher rate as we are witnessing the transition from conventional steel to recycled steel and green steel products, mainly due to growing concerns about carbon emissions and favorable net zero policies. Conventional steel making leads to larger amount of greenhouse gas emissions with coking coal used as a source, whereas recycled steel production leads to lower set of emissions with coal power, even with coal power, and green steel with hydrogen or renewable electricity as a source produces cleaner steel products compared to other two steel production processes. Next slide, please. So talking about the market dynamics in sustainable steel industry, rising developments in green hydrogen based direct reduced iron technology is one of the major trend shaping up the industry, whereas high production costs of green hydrogen and green steel is one of the major challenge that is resisting the market growth. But the cost is expected to come down in the upcoming years with the industry scale up. Rising demand from building and construction, transportation, furniture and appliances, and other industries, along with rising focus towards ensuring supply of sustainable energy, is influencing the market growth. Next slide, please. Yes. So here we have listed some of the key players operating in the sustainable steel market, such as ArcelorMittal, Nippon Steel, POSCO, Tata Steel, and others who are also actively involved in the developments of sustainable steel. For instance, in September 2022, Nippon Steel announced to launch the cleaner steel product. Similarly, other players are also involved in other key strategic action areas such as product launches, mergers and acquisitions, partnerships, and others, contributing to the sustainable steel industry's growth. Next slide, please. Talking about the market outlook of sustainable steel, the global market is expected to grow to $795.8 billion market in 2031 from $327.3 billion market in 2021, growing at a CAGR of 8.97%. Building and construction is leading the market in terms of end use among other industries like automotive, aerospace, and others. China is at the forefront in terms of regional market of sustainable steel. At last, I want to say governments and companies are highly focused towards decarbonization of steel industry, and ongoing efforts to attain net zero objectives will greatly influence the sustainable steel industry's growth in the upcoming times. That's all from my end. Thank you so much. Back to you, Priyanka.
Thank you so much, Sachin, for the valuable perspectives you brought to our webinar. Now, I would like to invite Ms. Troy for sharing her thoughts. Your expertise would be a valuable addition to our webinar. Over to you, Ms. Troy.
Kia ora. Kia ora koutou. Good morning from New Zealand, Aotearoa. My presentation is going to focus on some of the key questions that arise relating to decarbonisation in the steel industry. First slide, please. So some of the emission levels that Sachin spoke of are really attributable to not only the manufacturing process involved in steel production, but also to the prevalence of steel in our lives. Steel is the world's largest material industry, and it plays a prominent role in our daily lives and is critical to national infrastructure. Next slide, please. So steel is obviously a core part of our built environment, our road, rail, and bridge systems, as well as our consumer goods, our automotive industries, our manufacturing and building and construction industries. Next slide, please. And that demand isn't going to decline. In fact, it's predicted to increase by more than a third through to 2050. And this is because not only of that demand for our core infrastructure, but also because of the demand for steel in evolving our transition to a clean energy economy. Next slide, please. So again, steel is part of our core infrastructure for that transition. It's part of our wind, wave, geothermal, hydro, and solar technologies. And so that transition is critically reliant upon steel production also, as well as emerging renewable energies, including hydrogen. Next slide, please. So one of the critical misconceptions around decarbonisation of steel is really the misconception that the CO2 emissions are arising from the burning of coal to create energy for steelmaking. That's not correct, because CO2 is primarily coming from carbon used as a reductant in removing oxygen from the iron oxides. Next slide, please. So if we look at a typical steelmaking process, which down the bottom is that primary steelmaking process, we basically take iron ore, which is iron oxides. We turn that into a more pure form of iron by removing the oxides from that iron oxide chemistry. And that's when the CO2 is produced. So the carbon is binding with the oxygen and CO2 is a byproduct. The iron is then transferred or purified into steel. And that process is the primary production process, and the most prevalent process for steel production in the world. And its scope 1 and 2 emissions are quite significant, so 1.4 to 2.2 tonnes of CO2 per tonne of steel produced. The less common form of steel production is what's called electric arc furnace production, which is based on scrap. So it's still that's post-consumer and pre-consumer recycled, and that's just basically melted into a new version of steel. And that produces around a quarter of the CO2 emissions that the primary production process does. Next slide, please. Unfortunately, currently no commercially viable alternative exists for coal as a reductant in bulk steel making, but that doesn't mean the industry is doing nothing. Next slide, please. In fact, there's a significant financial and commercial incentive for steel companies to decarbonise. This McKinsey report demonstrates 40% of steel companies' potential value is at risk, and that same report showed that some companies have up to 30% at risk. So that's a very significant incentive for change. Next slide, please. There's many opportunities to remove carbon. They range from operational efficiency improvements that probably provide incremental improvement. There's a holy grail of finding an alternative reduction process, as well as looking at the whole life cycle of carbon and putting it more into a circular economy. But Daanish, the next speaker, will speak on some of these in more detail. Next slide, please. So the common question is, why don't we just use recycled steel? And the reason for that is that secondary scrap availability is not high enough to meet the global demand for steel. And so even beyond 2050, we will still be reliant upon that primary production of steel. Next slide, please. Do science-based targets exist? The Science-Based Target Initiative is planning a collaborative project with the steel sector to develop a specific steel sector guide. However, it's not a simple matter of allocating a carbon emissions target for the industry and then dividing that by the number of tonnes produced per annum and then allocating those to individual steel mills. And the reason for that is the difference in those production methods. So if that was to be applied, then some steel mills would not have aspirational targets and some would have targets that are set that are just simply not achievable. Next slide, please. So the Net Zero Steel Pathway Methodology Project has developed guidance to provide a science-based target approach that would be specific to the different steel mills and the production processes. And it also accounts for some of the other issues associated with science-based targets, which include co-products being produced within the boundaries of the steel sector that are utilised outside of the steel sector. So, for example, some uses of slag, which is a byproduct of steelmaking. Next slide, please. Do alternative reductants exist? Yes, they do. And as I mentioned previously, this holy grail of hydrogen as an alternate reductant is the predominant focus of research globally. It's not a trivial exercise. The chemistry is very complex. And so in the iron making process, there's significant technical challenges that need to be overcome in order for that to be scaled up to commercial scale. And in addition, obvious global focus on developing clean hydrogen production. Next slide, please. The most advanced project in this area would be the hybrid project. And I won't speak about this in too much detail because I know Daanish is going to, but I just wanted to raise three things. The first one is that a key part of this project is the collaboration across the supply chain. So that includes the raw material suppliers, the steel maker, the energy producer, as well as government. The second thing is that this research not only covers the iron making process, it covers also the hydrogen production process, as well as the policy settings that are required in order for this to be successfully rolled out. And that's really important. And the third thing is that although they have actually produced green steel using this technology, it has only been at very small scales and only for very niche applications. So in this case, automotive. And its SSAB is not even anticipated to adopt this technology broadly for its own production until the mid-2030s. So this technology for a global application is probably at least 10 years away. Next slide, please. However, an indicative decarbonisation pathway for steel technology is one that's in my area of the globe, so BlueScope Steel, which is headquartered in Australia and the parent company of New Zealand Steel. So typically you would see a steel mill produce a publicly stated emissions reduction target. They would produce their baseline. They would look at adopting incremental improvements, as I spoke of previously, to reduce operational carbon. Then look to adoption of emerging technologies. They may invest in capital alternatives to maybe transition a blast furnace to an electric arc furnace production process. And then later on, post 2030, probably up to the 2040s, look at the adoption of those really transformational technologies being developed globally, for example, direct hydrogen reduction. And then looking at offsets to remove the remainder of this CO2 emissions. Next slide, please. So what you will see is a lot of research happening globally around alternate reductants. One that is happening locally in New Zealand is coming from the Victoria University of Wellington. And these types of research programs will be specific to the local steel production processes, the specific raw materials, and the policy settings that are in place in that particular geography. So for us, New Zealand has a very unique steelmaking process. Instead of iron ores, we use iron sands to produce steel. And so that requires its own unique research to be undertaken. And of course, those policy settings are really important. We're lucky in New Zealand because we already have a substantial component of renewable electricity, which is really required for that transition to a hydrogen economy as well. Next slide, please. So I guess what typically happens when we discuss steel decarbonisation, we focus very much on the manufacturing side. But of course, if we're going to transition to a low carbon and zero carbon future, we really have to look at the whole supply chain and what application steel is being utilised in, which is typically related to the manufacturing and building and construction industries. So we need to look at the whole life cycle of the steel as a product as well. Next slide, please. So in New Zealand, for example, steel is a leader already in New Zealand's circular economy. 85% of construction steel is being recycled. We don't currently have an electric arc furnace in New Zealand, but there has been a recent announcement by New Zealand Steel and our government to invest in developing an electric arc furnace process here in New Zealand. So we would start to see that 85% move up to 100% and come to a true circular economy. That's equivalent to 1% of New Zealand's total greenhouse gas commitment reductions. So it's a very significant project in terms of what that means for our commitments under various protocols. Next slide, please. So HERA, the Heavy Engineering Research Association, is an independent research association, and we do a lot of research on the supply chain emissions reduction. So one of the initiatives, for example, is developing the first material passport for New Zealand and Australia, which may not be familiar to many people. It's something that's more common in Europe. Where basically you look at a digital tracker for a steel right from production through to end of life. So it keeps a record of the steel's initial qualities at production, the uses it's been applied to, any kind of events that it's experienced. For example, a seismic event would be relevant in New Zealand, and that creates basically buildings that become banks of materials that are then available at end of life. Of course, extending lifetimes of core infrastructure is really important. So, for example, in New Zealand, we have under the building code a requirement for structural steel to be designed to last 50 years. If we extend that out to other design phases to make sure that it's designed to have a lifetime of, say, 100 or even 200 years for a bridge, for example, then obviously we have impacts in terms of decarbonisation because that carbon is being amortized over a longer period of time. And of course, circular design is really important. So we've got a research project where we are developing a global first design guide for architects, designers, and engineers to design buildings for reuse and to reduce carbon across modules A to D, so right from manufacturing through to end of life. And of course, all of these initiatives are important on the decarbonisation journey. And I will hand back now. Thank you.
So thank you so much, Ms. Troy. Please accept our sincerest appreciation for the outstanding presentation you made on sustainable steel. Now, I would like to invite Mr. Daanish and his team to share their valuable insights and enlighten us with their expertise and knowledge in sustainable steel. Over to you, Mr. Daanish and team.
Thank you for joining us today. We are excited to present on the topic of green steel alongside my colleagues Harasis and Siddhi. Our next slide, our presentation is divided into sections: drivers, technologies, green steel initiatives, challenges, and finally conclusion. Next slide, please. Steel production contributes about 7 to 8% to the carbon dioxide emissions, releasing on an average approximately 1.5 ton to 2 metric tons of carbon dioxide for every ton of steel produced. Now let's explore the key drivers for green steel. Harasis, please take over.
Next slide, please. Here are listed the various drivers of green steel. Next slide, please. Starting with the first one, which is the various climate accords. It includes the Kyoto Protocol and the Paris Agreement. One important element of the Kyoto Protocol is the establishment of flexible market mechanisms, which are based on the trade of emission permits. Paris Agreement is a bridge between today's policies and climate neutrality before the end of the century. And the key elements of this agreement are the nationally determined contributions, global stocktake, climate finance, technology transfer and capacity building, transparency and accountability. Next slide, please. The other driver of green steel is the automobile industry. The auto industry accounts for around 12% of global steel consumption, and car makers are also turning to green steel as a way to drive down carbon dioxide emissions in automobile production. And various companies like Volvo Group, Mercedes-Benz, BMW, General Motors, and more others have taken various steps in this regard. Next slide, please. The other driver of green steel is the measures in developed countries, which include the EU's carbon border adjustment mechanism and carbon pricing. The EU's carbon border adjustment mechanism's primary objective is to stimulate cleaner industrial practices in non-European countries while ensuring a level playing field in terms of environmental responsibility. Carbon pricing provides across-the-board incentives to reduce energy use and shift to cleaner fuels, and is an essential price signal for redirecting new investment to cleaner technologies. Next slide, please. The other drivers of green steel include increasing consumer activism and availability of green steel technology. As consumers are becoming more and more environmentally conscious and are actively seeking out sustainable products, various initiatives have come up, like the Green Building Council that promotes the use of sustainably sourced and produced materials, including steel. The availability of green steel technology fosters competition, innovation, and scalability while providing expertise and support to steel producers.
Thank you, Harasis. Siddhi will now present various technologies for reducing carbon dioxide emissions. Siddhi?
Yeah, next slide, please. Current technologies for green steel. We will be covering scrap-based steel making and hydrogen-based steel making. Next slide, please. In scrap-based steel making is a secondary steel making, which is also known as electric arc furnace steel making. It involves using recycled scrap metal as the primary raw material. The scrap metal is collected, sorted, and processed to remove the contaminants. It is then charged into electric arc furnace, which is lined with refractory material and equipped with graphite electrodes. A high electric current passes through the electrodes, generating intense heat and melting the scrap metal. The temperature in the furnace reaches around 600 to 800 degrees Celsius. After melting, refining processes are used to remove the impurities and achieve the desired steel properties. The another method, that is hydrogen-based steel making, is also known as DRI-EF reduction steel making, in which iron ore is reduced to metallic iron, that is DRI, using hydrogen gas at lower temperatures compared to the blast furnace methods, that is nearly 800 to 1000 degrees Celsius. DRI is melted down and refined in an electric arc furnace, similar to scrap-based steel making. The refining process removes impurities and add alloying elements to achieve the desired steel properties. The molten steel is then cast into various shapes. Hydrogen-based steel making is still in the early stages of development, and it requires further research and technological advancement to become the commercially viable on large scale. Next slide, please. Green steel technology in the lab. Next slide, please. Traditionally, fossil fuels are essential in steel production. Most steel making starts in a blast furnace where coke reacts with iron ore, a mixture of iron oxides and other minerals. The reaction pulls out the oxygen, leaving behind liquid iron, and carbon dioxide is released. Next slide, please. But here comes Boston Metal steel making process, which was developed by MIT material researchers Donald Sadoway and Antonio Eleanor in mid-2000s. Boston Metal is a startup building a direct scalable steel decarbonization solution. Next slide, please. Boston Metal's new approach, that is molten oxide electrolysis (MOE), which replaces carbon with electricity to remove oxygen. A cell filled with dissolved iron oxides and other materials is heated by electricity to 600 degrees Celsius, which melts everything into a hot oxide soup. Electricity drives the oxygen removing reactions, resulting in molten iron at reactor's bottom and the emission of oxygen gas instead of carbon dioxide. The impurities are mostly excluded. This enables MOE to extract valuable metals from the low concentration waste materials. Next slide, please. Currently, the main challenges in transitioning to larger reactors is the stability of the inert anode. This inert anode is made from a mixture of steel and chromium. The anode's role is to facilitate the movement of electricity through the cell not participating in the reaction. However, if conditions such as current distribution and electrolyte chemistry are not properly balanced, the anode tends to degrade rapidly. They have completed a pilot reactor using anodes for a ferroalloy production, with plans to convert it for steel making. Next slide, please. The other technology is a hydrogen plasma. Hydrogen plasma is a special form of hydrogen gas in a plasma state which have benefits like lower activation energy and the reduction of iron oxide compared to the pure hydrogen. The reduced heat loss from the reactors lead to the cost saving up to 20% compared to blast furnace. Next slide, please. In other technologies for reducing carbon footprint, we will be covering carbon capture, utilization and storage, that is CCUS. CCUS refers to the technology that enables the carbon dioxide emissions from the large point sources such as power plants, refineries, and other industrial facilities, or the removal of existing carbon dioxide from the atmosphere. Next slide, please. Storage and utilization. Next slide, please. The main methods for capturing CO2 are post-combustion, pre-combustion, and oxy-fuel combustion. Post-combustion technology separates carbon dioxide from the flue gas by using a chemical solvent, for instance, after the fuel is burned. Pre-combustion method involve converting the fuel into a gas mixture consisting of hydrogen and CO2 before it is burned. Once the CO2 is separated, the remaining hydrogen-rich mixture can be used as a fuel. And finally, oxyfuel technology involves burning a fuel with almost pure oxygen to produce CO2 and steam, with the released CO2 subsequently captured. Post-combustion and oxyfuel technology can be fitted to new plants or retrofitted to existing facilities that were originally built without it. Pre-combustion methods require larger modification to the operation of the facility and are therefore more suitable to new plants. Currently, the operational facilities fitted with CCUS can capture around 90% of the CO2 present in the flue gas. It is technologically possible to achieve the high capture rates, and the research is going on to reduce the cost of doing so. Next slide, please. The CO2 that has been captured, it is compressed into a liquid state and it is transported and then injected into deep geological formations. And input for commercial products and services. But the climate implications of this are not clear-cut and it requires careful examination. Next slide.
Thank you, Siddhi. There are two major technologies for green steel production. The first is the well-established scrap-based method, which capitalizes on the inherent recyclability of steel. Electric arc furnaces have shown significant improvements in technology, matching blast furnace-based steel for many applications, including for the automotive industry. Electric arc furnaces emit approximately one-third of the carbon dioxide produced by blast furnaces. When combined with renewable energy-generated electricity, carbon dioxide emissions can be further reduced. The baseline for green steel can be set at about 400 kgs of carbon dioxide per metric ton of steel produced. With electric arc furnaces powered by renewable energy, this is achievable. However, due to the limitation of scrap availability and increasing steel consumption, there will still be a need for iron ore-based virgin steel. Hydrogen as a reductant shows promise in this area, moving from concept to pilot and trial productions. When combined with green hydrogen produced from renewable energy, it can reduce carbon dioxide emissions by up to 95%. There is also ongoing research into the electrolysis of iron ore, though it currently remains in the lab stage. Nevertheless, it could surpass hydrogen if its own production challenges are overcome. It may be noted hydrogen faces challenges such as high infrastructure costs for creation, storage, and transport. In the case of carbon storage, this may only delay the inevitable because it does not address the root cause of emissions, though it allows for the retrofitting of blast furnaces. In general, every effort to reduce carbon dioxide emissions, whether big or small, is an important step forward. Now let's explore the green steel initiatives that are currently underway. Harasis?
Let's start with the green steel initiatives in Europe first, which include the hybrid by SSAB, Salcos by Salzgitter, and many others. Next slide, please. No, previous slide. Yeah. SSAB has joined forces with various other producers to create hybrid, that is an initiative endeavoring to revolutionize steel making. Using hybrid technology, SSAB aims to replace coking coal, traditionally needed for ore-based steel making, with fossil-free electricity and hydrogen. Salcos by Salzgitter is another initiative. Salzgitter has joined forces with partners from industry and research to lay the foundations for virtually carbon dioxide-free steel production. ArcelorMittal is also investing in a broad range of initiatives to reduce carbon emissions from the blast furnace. Their initiatives range from the flagship smart carbon project like Torero and Carbalist to capturing hydrogen-rich waste gases from the steelmaking process and injecting them into the blast furnace to reduce coal use. And there are various other initiatives taken by other companies like Carbon to Chem by Thyssen and Salzgitter, HL Cerna by Tata Steel, H2 Future, and so on. Next slide, please. Moving on to green steel initiatives in other parts of the world. Various companies, for instance, China Bao Group, is pursuing the use of hydrogen-enriched carbon recycling blast furnace, green hydrogen fueled metallurgy, large-scale use of recycled steel, CCUS technology, and other routes to achieve carbon neutrality. POSCO in South Korea is using HYREX technology for hydrogen-based steelmaking process, where HYREX stands for hydrogen reduction. And there are other companies like Nippon Steel in Japan, Kobe Steel, Tata Steel, Fortescue and China Bao, Rio Tinto, and many others who have taken various initiatives in this regard. Next slide, please.
Thank you, Harasis. Europe, particularly Nordic countries, is at the forefront of the hydrogen route compared to the rest of the world. Question is the energy costs and whether government subsidies allow the optimum solution to emerge, which is the decoupling of iron making to countries with lower energy costs and abundance of iron ore. The United States, thanks to many mills with electric arc furnaces adopted early in the 80s, has a lower carbon dioxide footprint compared to other regions. Electric arc furnaces in the United States contribute to 70% of steel production, compared to approximately 30% globally. China is also collaborating with iron ore mines on the direct reduced iron via the hydrogen route, which is understandable given their status as the largest iron ore importer. While your Western countries excel in innovation in the labs, China stands out for its rapid adoption of technology, and once they find stable technologies, they are likely to commercialize at large scale. Due to their top-down government policies and extensive renewable energy capacity. Speaking of renewable energy in China, China added 62 gigawatts of solar energy and wind power capacity in the first 4 months of this year. In comparison, the country added only around 26 gigawatts during the same period in 2022. That has brought non-fossil fuel generating capacity to about half of the nation's total power mix. Around 80% of the new power capacity added this year so far comes from renewable sources. Now let's discuss the challenges and conclude our presentation. Harasis?
There are various challenges to green steel. For instance, there is lack of adequate infrastructure, including hydrogen production, storage, and transportation facilities. Ensuring an adequate supply of high-quality scrap metal and establishing efficient collection and recycling processes is another challenge. Shifting to green steel requires overcoming the legacy of sunk cost associated with existing infrastructure and equipment. The higher cost associated with hydrogen-based direct reduction process and hydrogen infrastructure costs also add to the challenge. Next slide, please. The other challenges to green steel include political and macroeconomic factors. For instance, the uncertainties in policy frameworks, regulatory support, and market conditions. Also, there is lack of consensus on the definition and standards of green steel. The cost of producing green steel, particularly in comparison to traditional steelmaking methods, is higher due to the use of raw material input in the form of DRI from hydrogen as a reductant. The current landscape suffers from a limited number of technology providers with the necessary expertise and capacity to support large-scale implementation. Next slide, please. Moving on to the conclusions. Next, first of all, we have is the equity of rules for countries in the developing world. Given the disparities evident in consumption patterns, the distributional implications of climate response strategies are critically important. There needs to be a definition of green steel with common buy-in, as the adoption and implementation of sustainable practices in the steel sector is greatly aided by definition of green steel that have widespread support. Government support also plays a crucial role in promoting and advancing green steel practices. Also, there needs to be strengthening of global accords, as the development and acceptance of green steel practices can be considerably aided by the strengthening of global accords. These global agreements set uniform standards and regulations for the manufacturing of green steel. Finally, there needs to be the spread of technology for green steel, as it plays a crucial role in advancing and promoting the adoption of sustainable practices in the steel industry. Also, there needs to be holistic view of the entire supply chain in steel making, as today's supply chain is more extended and complex than in the past. So to develop an efficient and effective decision-making process, it is necessary to have full visibility over each one of the segments composing. Next slide, please.
Thank you, Harasis. So there's a wide range of technologies available to reduce the carbon dioxide footprint in steel making. There is also research happening for substituting coke in the blast furnace with biomass, municipal waste, and even rubber tires. Microbes are being researched to improve iron content in low-grade iron ore. Access to renewable energy is growing across the globe, and byproducts from steelmaking can and are being utilized to further reduce the environmental impact. The spotlight is currently on hydrogen as a transformative solution for green steel. However, it is important to note that the creation of hydrogen can result in carbon dioxide emissions unless the energy used for production of hydrogen is sourced from renewable sources. Hydrogen is currently priced at around $8 per kg and must decrease to below $2 per kg and come close to $1 per kg to become a more viable option for widespread adoption. Government intervention will be crucial to subsidize green steel production and for the necessary hydrogen infrastructure. The transition to green steel through the hydrogen route will require a significant investment of around $3 trillion globally. By 2030, steel production via the hydrogen route will likely be modest, with less than 5 million tons produced in Europe, which is less than the 5% production within Europe, and time is not on our side with respect to climate change. For emerging and developing economies, it is essential to find fair and equitable solutions as they need to develop their own infrastructure without bearing excessive costs. Green steel production through the hydrogen process can add over 25% to the cost, which may be unaffordable for many countries facing pressing socio-economic issues. This is apart from the cost of creating an infrastructure for hydrogen. To achieve meaningful carbon dioxide reduction, the steel industry must consider the entire supply chain as per Scope 3 and not solely focus on the steel-making process. To achieve widespread decarbonization, a multi-pronged approach is necessary involving various technologies tailored to each country's geography and resources, along with technology sharing. Addressing these challenges requires global cooperation, which is hindered by geopolitical tensions and lack of unified, consistent policy agreements. We certainly live in challenging times. Thank you.
Thank you, Mr. Danish and team. We offer our deepest gratitude for sharing your knowledge and enhancing our webinar with your expertise. Now, I would like to invite Coyle for concluding notes and providing some insights on our AI-based platform. Over to you, Coyle.
Thank you, Priyanka. First and foremost, I extend my gratitude to Troy, Danis, and team and Sachin for shedding light on the crucial topic of forthcoming era, the sustainable steel. The insights shared were truly enlightening. To summarize, it is evident that achieving a net zero target for carbon emission is no longer optional. And to accomplish this, we must embrace green and low carbon emitting alternatives. As the speakers rightly pointed out, that steel making process is highly energy intensive and contributes significantly to carbon emission. Thus, the urgency to shift towards sustainable option cannot be overstated. During the webinar, two key approaches were discussed to reduce the steel production worldwide. Firstly, the recycling of steel scrap is a valuable strategy that can substantially mitigate the steel using steel environmental impact of the manufacturing. And the secondly, the adoption of greener methods such as producing steel using green hydrogen and renewable electricity holds immense potential in curbing carbon emission from the steel manufacturing industry. By adopting these substantial and sustainable practices, we can pave the way towards a more environment friendly and responsible steel manufacturing industry. Now, moving forward to the next slide. So the slides includes the key takeaways. That includes the net zero strategies by several economies, and several companies are focusing on the development of sustainable process for manufacturing green steel. And other takeaways include the transition from conventional to greener energy, growing focus towards steel scrap availability, rising investment in green steel, and so on. And as you can see on the screen. Now, moving forward to the next slide. As you can see, we have built up quite expertise and knowledge in this domain. As you can see on the screen, a lot of our research is focused on green technologies and sustainability. As you can see on the left side of the slide, we have a recently published list of report such as the green hydrogen market, carbon capture utilization and storage market, water electrolysis market, green ammonia market. And we also have on the right side, as you can see, some of our upcoming report that are already in publishing phase, such as a biomass-based hydrogen market, sustainable polyolefin market, biobutanol market, and so on. So these are some of our published or in publishing phase reports. So in case you wish to see the sample of market intelligence report on any of these topic, you may ping on the chat and our team will get back to you soon. Now, moving forward to the next slide, our proprietary platform Insight Monk is a one-step solution for customers looking for syndicate reports, company profiles, expert insights, key players, data, markets, statistics, expert consultation, noise-free search on deep tech topics, and a lot more. It offers a large set of relevant data cured by our internal and network experts and is readily available for access as per bespoke needs. Insight Navigator is a market intelligence assistant for Insight Monk. Specializing in deep tech industries, it provides insights and data on various themes such as healthcare, advanced materials and chemicals, aerospace and defense, agriculture and food tech, electronics and semiconductor, energy, and sustainability. Our colleague will put the link here as we speak on this chat, and you can go and log in by yourself. Once you register on it, our team will reach out to you. So that's all from my side. And for the Q&A round, I'd like Priyanka to take the lead. Over to you, Priyanka. Thank you very much.
Thank you so much, Coyle, for explaining about our AI platform. So, with this thought, let me conclude today's session and I declare the forum open for any questions from the listeners. I request the listeners to kindly type in the questions and I'll be happy to pass the questions to the esteemed speakers. So while the process of webinar, I received few questions. So the first question is for Ms. Troy. The question is, has any steel company done the full-scale blast furnace operations with biochar, biomass-based, replacing coking coal?
No, not that I'm aware of, but certainly I would suspect almost all steel producers are involved in research to replace at least part of their metallurgical coking coal with biochar. And I am aware of several in our region that are doing that research in collaboration with research organizations to deliver that. But nothing that I'm aware of that is fully transferred at the moment.
Okay. Thank you so much for your answer, Ms. Troy. So the next question is for Mr. Daanish and his team. The question is, which are the emerging unique technologies that are expected to come up in the upcoming years, which would be helpful in steel decarbonization?
I think, of course, hydrogen is one which is, if once the cost of hydrogen comes down, it could scale up. The other one is, of course, electrolysis, which is the Boston Metals project that's happening, that also shows promise once it overcomes the present challenges that it faces. These two are the most important initiatives that look like that could scale up. But there is a question of time. It will take maybe another 10 years, 15 years, but we can't wait for those 15 years. So I think a lot of the mills and will be setting short-term goals in terms of reducing the carbon dioxide, especially in the maybe in the emerging markets and the third world markets. One is, of course, electric arc furnaces will keep rising, but there is a question of developing the infrastructure of collecting the scrap, which is not there compared to the developed countries. In India, we have started setting up scrap yards. There's the government incentives, and the mills are also doing it. So I'm hopeful that electric arc furnaces will grow, particularly in India, which will make a big difference because India is now the third largest producer of steel. And all those little small research that's happening across the globe, like biomass, biochar, using tires, wherever coke can be replaced, that will happen. So it will be a gamut of technologies which are happening, and something like hydrogen electron be a game changer once the costs come down. And the costs can only come down once the infrastructure is built and the economies of scale happen. So we'll have to give it some time for that to happen. I hope I've answered that. Yeah.
Okay. Thank you so much, Mr. Daanish, for your answer. So there is another question for Ms. Troy. How can we ensure a consistent and reliable supply of high purity hydrogen for green steel production, considering the constraint of hydrogen production, storage, and transportation?
That's a really big question. And as I said earlier in my presentation, it really involves collaboration between industry and government because it requires higher level commitments, national commitments to renewable energy targets, because it's really the renewable energy component that creates the ability to create green hydrogen. So that is a much more complex situation where it's really around the political scenarios for each geography to resolve. Obviously, some countries, just by the nature of their ability to utilize and to create renewable energy, they will be in a better position than other nations. So I read a report recently around renewable energy production. So China, India, Russia are all emerging as the top 3 renewable energy generating countries. And so I would suspect that there's going to be an advantage there. I know Australia is looking at developing itself as an exporter of renewable energy. So I think that's how we will start to see that change, is that the focus will really be on the renewable energy generation first and the hydrogen production second.
Thank you so much, Ms. Troy. So maybe the last questions for today's session. Question is, which are the major initiatives being taken that would be helpful in bringing down the cost of green steel? So would Ms. Troy or Mr. Daanish like to volunteer this question?
Dr. Troy, maybe you can answer that.
Yes. So for example, BlueScope has calculated that or estimated that green steel production would be 6 times more expensive than blast furnace based steel production. So it's a significant cost differential. And really they have been focused on collaboration with government to invest in that hydrogen production capacity being specifically created geographically close to the steel production location. So again, it comes back to those government industry collaborations around strategically creating that hydrogen infrastructure, locating it close to the main users of the green hydrogen. But really, I mean, it's inevitable that the cost of hydrogen production will come down. We've seen that with almost all energy production technologies. Most recently, solar would be the most common example. It just, as the technology evolves, obviously the costs will become more competitive. Daanish, I'll transfer back to you.
I think what you're saying is absolutely correct. It's basically economies of scale as the infrastructure comes in and the more increasing costs will come down. I think there's also other way to look at it, especially in Europe, is with the high energy costs. They could look at decoupling of the iron making, which like the Americas, the cost of energy is lower, there's a lot of abundance of iron ore. But these are all decisions which are very difficult to make because steel making is also very emotional and everybody wants to control the entire process end to end, right from the iron making to the downstream operations. So very difficult. There is also, we've seen during COVID, supply chains being disturbed, and even steel making to an extent is a national security importance. So I guess it'll take some time for the cost to come down. But countries which have access to renewable energy will more likely have lower costs, like the Nordic countries. And the process, I think, there's no switch, I think. Okay. Thank you. Dr. Troy? I hope I've answered that. We'll have to be patient. It's going to take years for the cost to come down, I think.
So thank you so much, Mr. Daanish and Ms. Troy. So there is another question which is coming up, that is how industry is trying to solve the problem of inadequate recycling technologies and incomplete separation of impurities in scrap steel. So Mr. Daanish or Ms. Troy would like to volunteer this question?
Dr. Troy, would you go ahead?
I'm not really aware of a significant issue with the recycling technologies. As I had in my presentation already, 85% of construction steel is being recycled. So, and that would be the major contributor of steel scrap. And what brings that recycling rate lower across all types of steel scrap is really the consumer goods. And that's really much more down to consumer behavior around recycling. And so I would say that is there's more focus on circular economy, people start to understand the importance. Once a country has electric arc furnaces available to it, you can make much more of a communication strategy around the importance of recycling of steel. But I'm not really so aware that that's a significant issue in terms of available scrap. Daanish?
I think the technologies for scrap are there. It's that in the case of India, we don't have a very good infrastructure for collecting, sorting, and using the scrap. But it's a matter of time because we have the policies in place. So it will happen. The only problem I see in the case of scrap is that it's becoming increasingly something which has to be protected from being exported. It's like Europe is putting barriers for export of scrap. So that may be a hindrance to a country like India, which imports a lot of scrap, including Turkey, if the scrap stays within Europe. And what happens? We don't have enough scrap for electric arc furnaces. And the scrap prices will go up within Europe. So these are all pushes and pulls that every country is facing on how to go forward.
And just to further add to that, because I know that the metal recycling industry will get annoyed with me, but I guess we also have to look at scrap as a commodity, a valuable commodity, and particularly in jurisdictions where there are electric arc furnaces, there is a very strong and viable industry in itself in the steel recycling.
Absolutely. The only part is that we share a common. So, if Europe or one country controls the scrap, the other country may not have sufficient scrap and start increasing the blast furnace usage, and again, doesn't solve having lower carbon dioxide emissions. So everything has to be done at a global level. Like, that's the more difficult part, I think. Yeah. Any other questions over there?
No, that was the last question. Okay, so thank you so much, Mr. Danish and Ms. Troy, for your insightful answers. I would like to thank all the esteemed speakers for today and thank you everyone for being the part of this webinar. And all the questions which are remain unanswered will be answered through our blog post or through questionnaires. Thank you so much for attending.
Thank you.
Thank you so much, team.
Thank you so much.
Thank you so much.
Thank you.